In this video, we'll do a quick review of this electronics model inside of Simcenter FLOEFD XT. Here we are in FLOEFD XT. In this project, we have this electronics device, and here we already have the full project defined. We have the boundary conditions, the materials, the power already all assigned. So here I just wanted to show you what the complete project in FLOEFD XT looks like. And then in the following videos, we will be creating this project from scratch in Simcenter FLOEFD. Okay, so we'll be replicating this same kind of project in Simcenter FLOEFD. Now in FLOEFD XT, in order to start the project, we would go through the wizard where we specify the name, we specify the units we want to use, the types of physics, such as internal, external flow, direction of gravity, steady state or transient analysis, the default material and fluid selections, and so on. And this process is very similar in Simcenter FLOEFD. Here in this project, we have two PCBs, printed circuit boards, and these were imported through FLOEFD XT's EDA bridge. Now, if you're not familiar with EDA bridge, that is a bridge that allows you to import everything that you need for a thermal simulation from an EDA tools export. There you can assign different powers for the components. You can define the fidelity of the board itself, so it can be just a simple block with an average material property, or a layer board, or a smart PCB, or on the most detailed side, a fully explicit board with all the traces and vias represented in CAD geometry. And you can import this all into FLOEFD XT. So there's other capabilities within the EDA bridge window, but that's for another presentation. And this whole process is also very similar for FLOEFD. Here in FLOEFD XT, we also imported two gap pads, and that was done through FLOEFD XT's library. Now in FLOEFD, it's going to be a different type of process to do that, so we'll go over that later on. One thing I want to mention is the way to handle overlapping geometry is different between FLOEFD XT and FLOEFD. In this example, we have the gap pad and the enclosure overlapping in this area. FLOEFD XT will decide which object will take precedence in that overlapping space by utilizing the tree hierarchy. FLOEFD XT solves from top to bottom. So in this case, we first see the gap pad in that area, then the solver solves from top to bottom in the tree, and it sees the enclosure is sharing the same area. So in this case, because the enclosure is below the gap pad, the enclosure material will take precedence for that overlapping space. In FLOEFD, the way you tell the software which material to use in overlapping geometry, it is handled a little bit differently. In FLOEFD XT, you just move the components up and down in the tree hierarchy, but in FLOEFD, you have a separate window called Materials Priority, where you specify which materials should take precedence based on the priority list that you can modify. Now, this will be more efficient for complex models that have a lot of objects and material assigned. It will be a lot more efficient in FLOEFD's method of handling overlapping geometry. In FLOEFD XT, we have this Components tab where you have the properties, and you can assign what material it has and assign a local mesh. This all can be done in FLOEFD as well, but it is handled a little bit differently, so we'll go over that in detail later on. Alright, and in FLOEFD XT, in this project, we have the materials, some of which came from EDA Bridge, some came from the library. The thermal attributes, these came from EDA Bridge, and at this point, it would be ready to solve for thermal and fluid simulation. In the next videos, we'll show how to set up the same kind of project in Simcenter FLOEFD. With FLOEFD XT 2412 and FLOEFD 2412, you have the ability to export the project from FLOEFD XT into FLOEFD. The way you would do that is if you export a XT XML project from FLOEFD XT, and then import that file into FLOEFD. So here I have a new saved assembly in Creo, and in FLOEFD, if I go to Tools, XML Import, select the XT.xml project file that I exported from Flotherm XT and hit Open. And it imports the Flotherm XT project into FLOEFD. So if we inspect the tree here, we can see it imported the computational domain size, the materials, the heat sources, radiative surfaces, the 2 resistor components, and goals. Now, at the moment of this version, it does not import the localized meshes that were created in Flotherm XT. Switching back to Flotherm XT, we also have the ability to export individual components here. If we right-click on this PCB, for example, and go to Export XT XML Assembly, save that file, and then in FLOEFD, go to Tools, XML Import, just as before, select that XT.xmla file we just exported of the PCB, hit Open, and here you can see it imported the CAD geometry along with all the features already assigned appropriately to that geometry. Going back to Flotherm XT, I wanted to show you how you can export the Flotherm XT's part library items into FLOEFD. Very first thing you must do is you can't have any loaded project in Flotherm XT. So here we'll close this one. Now in your Flotherm XT's part library, you can right-click either on a folder or on an individual item here. And we have the ability to export to XT.xml or XT.xml as component. The XT.xml as component just adds an additional section in the file for the package metadata. This is used for that new library replacement feature in both Flotherm XT's and FLOEFD's EDA bridge in 24.12. Okay, so as I mentioned, you can export the individual items here, or you can export a folder containing all the items all in one go. So for example, let's export this folder. We'll right-click, hit Export to XT.xml, give it a save location here, library, hit OK. And as you can see, it opened up that geometry, which is why we had to have no project loaded in the first place. Here we hit OK. And now if we look at the folder, we have both of these items from that library folder saved as an XT.xmla file, which then you can import into FLOEFD just as we saw earlier. In this video, we'll go through setting up the FLOEFD project. First, make sure you launched FLOEFD for Creo using the appropriate executable. And that's found under your Start, Apps, and scroll down to Simcenter FLOEFD for Creo. This will launch your Creo software with the FLOEFD embedded inside here. Now also note, you must open an assembly with at least one part in Creo in order for FLOEFD to be active here. So to start, first I like to unselect the Creo displays here to make the geometry a little bit cleaner. And then we have two options to start the project of FLOEFD. In the wizard, you'll be guided through which physics you want to use, direction of gravity, your ambient condition, default materials and fluids, and so on, which we'll go through here. The second option is to select New, which allows you to select a predefined template. For example, once we go through the wizard, we go through the mesh settings, and even post-processing, you can later save this template by going to Project, Create Template, and in another model, you can just load that template and you'll have all your features and boundary conditions and everything set, ready to go as you set it before. Okay, So in this, we have an assembly here with the enclosure and the two gap pads. We will import the PCB later on through EDA Bridge and then align the gap pads to that PCB. All right, but for now, let's go through the wizard. Here you can name the project, hit next. You can select which unit system you want to use. You can also modify some of these predefined ones, customize it, and save it for future use. So for example, typically for electronics, I like to work in millimeters and Celsius. For volume flow rate, I like to use CFM. Then we hit next. And here you can choose which physics you want in your simulation. So for this one, we will do fluid flow and conduction. Notice also we have structural, electromagnetics, and free surface. So these are extra physics you have in FLOEFD that were not available in Flotherm XT. So for here, we'll also select radiation. We can change the environment temperature to be, let's say, 30 degrees Celsius. We want to turn on gravity as well. And we can see the direction of the vector. Let's change that to X direction. So I'll just copy this, put that to 0, and paste it here. Okay. For analysis type, this is external, meaning we'll have fluid flow outside of this enclosure as well as inside. For geometry recognition, there is an extra option here that's not available in XT, which is called Mesh Boolean. And that is an extremely powerful geometry recognition process that allows you to work with very complex models and also unclean geometry. So for example, if you had CAD geometry that was translated from one CAD tool to another, some of the geometry is a little bit broken, Mesh Boolean can handle that fantastically and process that geometry a lot more efficient and faster than the previous options. So if you do have complex geometry, dirty geometry, or just many parts, definitely try and use Mesh Boolean operations. All right, we'll hit next. Here we can select the fluid. So you can either double click or hit add here. Next. Here we'll select the default material. So let's just pick a random one here. Let's do metal aluminum. Here we can select the default wall radiative surface. So let's select one. And this opens up your engineering database. And I'll go over engineering database in more detail later on. But essentially this is where you can store information about things like material properties. In this case, we see radiative surfaces filtered here, so that's all we see. There's other things like true resistor component information and so on. All right, so we can go to predefined, and this comes with your FLOEFD install. So let's just select one here. We'll do aluminum. Under item properties, we can see the emissivity coefficient, 0.27 here. So we can select that. And then, of course, you can modify it. So, for example, you can create a new one under user defined. You can also copy it, go to user defined, and paste it here. You can name it something else and then change your properties here. Okay. But for us, let's just choose that and hit OK. And now all the objects in our simulation will be aluminum for our radiative surfaces. Later on, you can select different surfaces to have different radiative surface properties as well. And lastly, here we have our initial and ambient conditions. So here we can change the temperatures, for example, and then for solid temperatures as well here, let's say 30 degrees Celsius, and then we'll hit finish. Okay, so our project was created. We can see the project is here, and it created a computational domain. So at this point, we can go down the tree here and change the features for selecting certain materials on objects, boundary conditions, mesh settings, and so on. Let's now fill in the input data for this simulation. You can go from any order. You can start with mesh or boundary conditions. I just like to work from top to bottom. So let's start with the computational domain. After we finish the wizard, the computational domain was created. At this point, I like to adjust it to how I'd like it. As you saw, if you select it, the grab handles appear, so you can simply just stretch the computational domain that way. Or if you right-click and hit Edit Definition, you can input the size. Here you can also define whether it's a symmetry on each face of the computational domain. Now we can work here from the tree, hit right-click, edit, but a lot of the options are also available here in the ribbon. Typically you'll see me in the videos working from the tree, but they are available here. For example, the computational domain is right here as well. Okay, so let's adjust it quickly here. You can just grab the handles. If you click on Shift on your keyboard and then click and drag, both sides will be adjusted. And I'll adjust it on all sides here. That wasn't even, so let me just make that one there. And gravity is pointed into the X direction. So let's adjust the bottom here and then leave the top a little bit bigger for the natural convection air to get fully developed. Okay, once we are happy with the computational domain, we can just right-click, hide, no longer have to see it in the display area here. Alright, next down on the list, fluid subdomains. We're not doing any water cooling or anything like that here, so we don't need to introduce a second or third fluid, so we'll leave that. Solid materials. Here, let's define these gap pads with the solid material. We can do so by right-clicking on solid materials and hitting Insert Solid Material. Before I do that, actually, I should mention, if your CAD model already has material properties, you can import data from model, meaning it pulls in from the Creo material database. Now, if it has thermal material properties, then this could save you some time. But here, we'll do Insert Solid Material. And first, we need to select the objects. So a couple ways to do this. One, we can simply just select them here visually by clicking on them. And as you can see, it's being selected here. Or, let me start over here. You can go to your navigation tree here and just simply select them in the tree. For the material type, there's already some user-defined material I'd like to select that was saved in the engineered database. So I'll go ahead and select that here and hit OK. So now in our tree here, we can see that the gap pads have been assigned to this material here. And if you click on it, you can rename this material if you'd like to. Now for the enclosure, remember that we already defined a material for the whole model in the wizard, so we don't need to define that. Which, by the way, you can access all the settings that you set in the wizard under General Settings. So if you open that up, you can go through all the properties that you've changed in the wizard here. So your physics, your fluids, and if you don't recall what we had set, we had aluminum for the material. So everything that's not specifically defined under solid materials here will be aluminum. Next, we have boundary conditions. We're not going to insert any boundary conditions here for this model, but this is where you'd introduce some kind of forced flow, whether you're attaching it to a fan, for example, pressure openings, and so on. So we don't need that here. Next, we have radiative surfaces. Now recall, in our general settings, we already have a radiative surface for the whole model, where we selected an aluminum. And that's okay for me in this model, but let's say you did want to select different surfaces to have different radiative properties. You can do that here. You can select this face and select a different radiative surface here. Next, we want to set up our goals. And you want to set your goals for your parameters of interest in your project, right? So for example, let's say you have a die in your model. you want to know the average temperature of that die, you can set up a volume goal for that. And this helps you in multiple ways. One, you get to monitor the convergence of that goal as your model is solving. You get to see the value of that goal. A second benefit is that you can set your solver to stop once particular goals are converged. Okay, so this could decrease your overall solution time, right? So for example, if your die has already become steady state, the temperatures are not fluctuating, there's no need to continue to solve for maybe some fluid phenomena in the opposite corner of your model that FLOEFD is still trying to find convergence for. Also, you can use the goal to export the overall results and display them or export them to spreadsheets, for example, after the solve is done. So the available goals you have here are global goals. This will be for everything inside the computational domain. Point goal, you can specify a point on a particular area. Surface goals, volume goals, and equation goals. So equation goals can be used for something like, for example, the difference of something. So for example, your inlet pressure versus your outlet pressure, and you can specify an equation to subtract them so you can have your delta P. Here, let's specify some global goals. Let's do temperature solid for minimum, average, and maximum for everything inside this solution domain here. And notice that use for convergence is checked. So the FLOEFD solver will stop once these goals are converged. Another example here of a goal could be mass solid maximum. For example, let's say we were to change the geometry of these fins on this enclosure. The overall mass will change. So this, if we check this, it's a great way to monitor and export what was the total mass for that enclosure. Now let's discuss the meshing in FLOEFD. So it's the same underlying technology as in Flotherm XT. However, you do have more options for refinement, and it is set up a little bit differently than you do it in Flotherm XT. First, we'll look over global mesh, and then secondly, we'll look at how you would refine something in the more local level. So for global mesh, you want to right-click and do Edit Definition to open up the global mesh settings. By default, it will be set to automatic with a level 3 resolution. And we can check the Show Basic Mesh so we can see what that looks like. As we move the slider here, you can see the resolution change. We also have the option for minimum gap size. So this is calculated automatically based on the size of the model, the computational domain size, also any features you have set here where you chose any faces. It will look at those gap sizes as well and determine a size, but it's possible that's going to be insufficient to recognize some relatively small gaps, so you can check that here and input your value. Now let's look at the right view here. So as we move this slider, we can see the different levels of resolution. Now with FLOEFD's Smart Cell technology, within one grid cell, you can have up to 20 different control volumes. So you can have multiple fluids, multiple solids, all recognized by FLOEFD's Smart Cell technologies. And on the surfaces between the solid and the fluid, there are polyhedral cells that will be created. So let's just solve this and I can show you visually what that would look like with these settings. So if we check this off, we go to Run, we uncheck the solver, just have the mesh checked. We'll use all cores, which by the way, FLOEFD's mesher scales nicely up to 32 cores. We'll hit Run. We'll have a new window open up where it first prepares the geometry and then solves for the mesh. So just a couple seconds, it created 32,000 cells. Under results, we'll create a surface plot. And we'll use, and by the way, we'll go over post-processing later on in a future video. So for now, I'll go quickly just to show you the mesh. I'll use all faces. We'll do mesh solid color or fixed color. Under options, we want to make sure that use CAD geometry is off. So we're only seeing, or we're only visualizing the geometry that FLOEFD sees after it meshes it, rather than the CAD geometry from Creo. We'll hit OK. We'll also check off the geometry here. So this is how FLOEFD meshed it with the settings we had prior in the global mesh settings. Okay, so if we look at this, we can see how there's a polyhedral cell here representing that curvature. For everything else that is rectangular, it has the exact measurements of the original CAD geometry. All right, let's turn off the surface plot. We'll bring back the geometry by clicking on the display model geometry. Now let's say you want more options. The reason you might want to go into manual is if you have a very complicated model and you want more refinement options that you want to do manually, or let's say you want something more consistent where you want to keep the same settings going from model to model rather than have FLOEFD do its own thing. You can go to manual. First, you'll be presented with the basic mesh size. If you click here, you can just say I want 47 cells across in X direction, or you can just specify a size here. For a lot of electronics, you can kind of start off with 10 by 10 by 10 millimeters. It's pretty decent sizing. Depending on the size of your model and the refinement level you want to do, you can adjust accordingly. And then let's look at the options you have available here. So I'll uncheck them first. First one, refining level. So here we can refine all the fluid cells from level 0 to 9, all the solid cells, and the cells at the fluid solid boundary only, right? So for example, I had a model where I was simulating a fan and the fan blades, and so I wanted the tips of the fans to have a lot more refinement, so I used this feature. Now, to understand the level of refinements here, we have a great feature called display refinement level. So let's check that on. And let's look at the right view here. So the way that works is it takes one cell and splits it into 8 cells. Your basic mesh size is your level 0 refinement level. Okay, so in this case, that would be level 0 would be 10 by 10 by 10 millimeters. Level 1 would split that one cell into 8 cells. So each one of those would be 5 by 5 by 5 millimeters. All right, and now if we zoom in here, looking at this curvature, if we do level 2, it'll be split up into 8 more cells. Level 3, level 4, and so on. So this is a great way to display what the refinement levels are, right? So for example, let's say we want level 3 refinement. What we can then do is specify, for example, I want the solids in the whole model under global mesh to be a level 3 refinement. And we'll take a look at this again in our, when I do a localized mesh refinement. Channels allows you to refine channels between objects. And then we also have advanced refinements here. For example, we can do small solid feature refinements, curvature refinements, and so on. Okay, so I'll uncheck these. We don't necessarily need them for this model. I'll just keep it at a basic mesh and hit OK. Now, if we want to do a local mesh refinement, let's say we want to refine these gap pads. Let's pretend they're dies and we want refinement there, right? So you can right click on mesh, do insert local mesh, and then you have the option to pick objects, or you can just specify a location and just drag the arrows, and then you can select the mesh refinement options here. For this, we'll do the part selection. One quick tip is if you already have those objects selected in one of the features here under input data. So for example, I already know that I have the gap pad selected in this solid material. If I click this, in my selection here, it will populate everything that was associated with that solid material. Okay, so for here, I want to refine them maybe level 3. And if I'm not sure again, let's display the refinement level. Let's look at the right view and zoom in. And so level 3 would look like that. It would give me about 4 cells into the thickness of this object here. Okay, so I like that. I'm going to leave this at level 3. Hit OK. Let's go ahead and run this again and see what it looks like. All right, so now we have 114,000 cells. Close this window. Let's display this again, and let's also turn off the geometry. So yeah, you can see how much more refined these gap pads now are. So that's how you'd create a local mesh. All right? We don't need that refinement, so I can just right-click and hit suppress. And the next time I run this, it will have the global mesh settings only. At this stage, let's bring in a PCB with some components, and we will utilize the EDA bridge to do so. To activate it, go under Tools and click on EDA Import. Now, I already have an EDA bridge file saved, so let me open that. FLOEFD's EDA bridge is essentially identical to Flotherm XT EDA bridge. You have your abilities to change the modeling level of the PCB from compact, layered, smart PCB, fully explicit. You can modify each layer. Here we see a few components here with the power already assigned. These powers were assigned by using the thermal list import. So this is all identical between FLOEFD and Flotherm XT. The part I want to spend some time on is the new feature component library for FLOEFD EDA bridge. Now this is new with FLOEFD 2412. And with Flotherm XT 2412, the component library has also been updated to be used the same way as I'm going to show you here in FLOEFD. So first we want to point to where your components are stored. So in this case I have a couple of components stored under demo files library here, so I'll select that. Let's name this library name. I'll say library demo, and we'll add this library source. So now in the middle here we can see the packages that are available inside of that folder directory that I chose earlier. Now you can point to multiple library sources, so you can go through that same process under Add Library, and these directories can be local folders, but it also can be mapped network locations. And both FLOEFD 2412 and Flotherm XT 2412, they can point to the same library locations. Now these packages are saved in XT XML file format. So if we look at the directory here, these are the two packages that I have saved. They are under XT XMLA files, and these were generated in Package Creator. I also have that open here. Let me show you. If you're not familiar with Package Creator, this is essentially a tool that could very quickly create a thermal ready package and then export it into XT XML format. The way this works is you start with a wizard where you can select any type of package here, and then once you're finished with the wizard, you can go through the properties of the package and easily and quickly modify any properties you may need, and then export this to an XT XML file, where then you can import that directly into FLOEFD or use the component swapping in EDA Bridge. Now there's two methods to replace your component. One is manually, where, for example, let's say we want to replace our U25 component with this BGA 169 package that I have saved. So if I select it in the tree and then I check on this one from the library, I can hit replace selected. And now the little icon here changes, and under thermal, it shows you that it's now a library detailed component. The other method of replacing is to use replace matching. Here first you want to select which libraries you want to swap the components from, and then what kind of match criteria you want, whether it's from the package name, part number, thermal model ID, and then which ones you want to replace it with. Now if you have multiple matching library items, you can decide whether to use the simplest component or the best component with these checkboxes here. Okay, so again, this component library feature is new for FLOEFD 24.12 and not available in previous versions. Now, for the purpose of the demo, I'll just put this back to simple and transfer the assembly to FLOEFD. Now we have the PCB and components in our model. Through that EDA bridge transfer process that we did earlier, FLOEFD automatically created the CAD for the PCB and components, and it attached the features such as the material properties and the heat sources to the appropriate geometry automatically. So if we look at our navigation tree, you can see this assembly here, which contains the components and the board in this subassembly. Now notice that the material assignment and the heat source assignment is not in our main project here. It is under this branch called From Components. This From Components concept is important to understand in FLOEFD. It is FLOEFD's method for model reuse. So for electronics cooling, for example, it's quite important where if you want to reuse PCBs or components in other future FLOEFD models, you can use this From Components feature, which allows you to reuse those models. FLOEFD does not have a library like Flotherm XT. However, this From Components can kind of mimic Flotherm XT's library, where you have the geometry and the attached conditions that you can reuse. Okay, so if we look underneath this From Components branch, we see the PCB and components that we brought in from EDA Bridge, and this is a self-contained sub-project. So you can see the materials attached to each layer, the components, the heat sources attached to the components, the 2-resistor component. So being that this is a self-contained sub-project, we can right-click and do Open Project. Here we see our board and components, which were brought in from EDA Bridge. As you can see, it's a fully defined project, so we can independently solve it here in our sub-project as well if we wanted to. We see all the materials defined, the heat sources, the 2-resistor component. Any changes you make here will be updated in our main project. Okay, so there's 2 changes I'm going to make here in this sub-project. One is I want to add a goal for our 2-resistor component. So I'll right-click, do Edit Definition, and expand the goals. And I want to check on the junction temperature goal. Hit OK. Now I also want 2 variations of this project. I will apply different heat sources for our U1 component. So I'll go ahead and clone this project. Right-click, clone, and I'll rename this to U1 3 watts. Hit OK. Then I'll go down to our component, edit definition, change that to 3 watts. Hit OK. Now at the top here, we can see we have our 2 projects, the main project and the sub-project. I'll go ahead and save this sub-project. Oh, and actually, let's also remember to rebuild the project, then save, and then we can close this sub-project. And now if we look at our subproject here, we see we don't have the goal here updated. So what we need to do is right-click on From Components and hit Update All. And now the goal has been added. Now let's say I want to change this board to that other project with the 3 watts that I had created earlier. To do that, I would go to From Components, hit Add From Components, and here we have our main project, our sub-project, and if I expand this one, you can see the second 3 watt project that I created earlier. Select that, hit Add, close this window. Now if I expand this one, you can see it's been updated to that second project where I had a 3 watt heat source attached. Now my next goal is to reuse this PCB and have 2 PCBs in this model. So in order to do that, I will right click on the PCB and hit Clone with Geometry. So now if we go to our navigation tree, we have a duplicate, 2 subassemblies of the PCB and components each. They're laying right on top of each other, so that's why we don't see it visually. We will move them later. And in our FLOEFD From Components branch, we see 2 sub-projects here. Now let's say I want one of them to be 3 watts and the other one to be that second project where I specified 4 watts. To change that, I'll right-click on From Components, go to Add From Components, and I will change this one to the original, which was set to 4 watts earlier. Then I'll hit Add, close this, and now if we expand this, we see this U1 component is 4 watts, and then if we expand the other one, it is set to 3 watts. Another thing worth noting about this From Components, all these features can be moved or copied to the main project. So if you just right click on any of them, you can do Move to Project, and it will move it up here to your main project, where then you can modify the properties of the feature anytime here in your main project. Now remember, this From Components feature is not limited to the PCB and components using EDA Bridge only. This is just the current workflow used in this demo. But From Components can be used for any model reuse, right? So for example, let's say you have a FLOEFD project where you have some detailed component, maybe a heatsink on top, and then you have another FLOEFD project, let's say it's a computer case, and you want to reuse that component in heatsink. So first you would open up your case assembly, and then in Creo, you would go to Model, Assemble, Include, import that component and heatsink assembly. Then in FLOEFD, you would go to From Components, Add From Components. You'd see this project here, add it to your FLOEFD project, and then you'd have your component geometry, your heatsink geometry, as well as all the features such as materials and powers and so on already attached under your From Components branch. Since the last video, I aligned and constrained the gap pads to the PCB, as well as moved that second PCB 11 millimeters in the Z direction. So now all the geometry is placed in the correct location. Now let's talk about material priority. So if you have overlapping geometry, by default, the last material here under solid materials will take precedence. Now, if you want to modify that, you can go under Tools, Material Priorities, and change the material priorities here. The reason this list is bigger than the one we see on the left is because this includes all material from your project, including the sub-projects from components. In our model, we have these 2 gap pads, and they are overlapping space with the enclosure. Now you can go into the CAD and make these gap pads smaller so that the enclosure and the gap pad is adjacent, but it would be a lot easier to decide which materials should take precedence using this list here. So here we see the default material, which is the enclosure aluminum on the very bottom, and that will always be the case for all FLOEFD projects. The default lowest priority will be the material that you selected under general settings. So for us here, we want this overlapping space to be aluminum. So we will click on this and go ahead and click up and hit apply. Another feature here in material priorities is you can select this highlight geometry. So if you're unsure what's selected, you can now select the gap pad and see them highlighted. If we highlight the typical plastic package, it highlights all the components. The aluminum will highlight the enclosure, and so on. Okay, at this point we can hit apply and close this window. Now let's talk about Component Explorer. Component Explorer allows you to view, edit, and create new features for all your components in your model in this one area. So you have the ability to change the material, volume source, surface sources, printed circuit boards, 2-resistor components, and LEDs. So for example, if we look through our model here, let's say we want to change the material of our gap pad. We can see all our different materials from our engineering database here. The properties to the selected features is listed on the right side here. Let's say I would like to apply a volume source to this gap pad. All I'd have to do is double click here, type in a value, hit enter, and if I hit apply, you can see it was just generated in our FLOEFD feature tree here. I could have also, for example, created a 2-resistor component here. I could have just typed in a power value here and then selected a 2-resistor component from our engineering database here. Now, a lot of these components being displayed here are coming in from our sub-projects under From Components, and they cannot be modified here under our main project Component Explorer. So there's two methods to use Component Explorer for these sub-projects. One is open up the project individually, where you can use Component Explorer to create or modify the features of the components in that sub-project. Then you can save that sub-project, go to From Components, hit Update All, and it will be updated here in your main project. Or the second method could be just to simply move the features here under this sub-project into your main project. So all we have to do is expand that. I could select either individually or all of them at once. Right-click, move to project. Now that they are in the main project, you can of course modify them here, edit definition, but we'll go back to Component Explorer. And now at Component Explorer, you can modify them here just by changing the value. Now also, for situations like this where you have many values you can change, if it's easier for you to do in a spreadsheet, you can export this into a spreadsheet, and it would look something like this, where then here you can modify your features. In this case, we're looking at the volume sources, save this spreadsheet, export it, and then in Component Explorer, import it. It will update the different features that you've changed in your spreadsheet. Then you can hit apply, and it will apply all of them for your FLOEFD project. In this video, we will solve the model. So once all our features are set, we have our boundary conditions, heat sources, materials, goals, meshes all defined. We can go up here to the toolbar and hit run. By default, the mesh and solve will be checked. If you just want to mesh the model, you can do that. So in this case, it would just run a few seconds, and then you can inspect the mesh. But for me, I know I'm happy with the mesh, so I will keep the solve checked. You can decide which computer to run the solver on and how many cores to use. I'm on my laptop with 16 cores. I have some other things running, so I'll set it to 12 cores. FLOEFD's mesher scales pretty nicely up to about 32 cores, where anything after that you have diminishing returns. And the CFD solver scales nicely up to about 20 cores or so. And of course, it's model dependent, but on average, it scales nicely to about 20 cores. At least this is the case for the current 2024 versions of FLOEFD. Okay, and at this point I can hit run. But before I do that, I just want to point out also we have batch run available here. So if you had multiple projects here, you can queue them up here under batch run. Here you can specify the maximum simultaneous runs, whether you mesh it, solve it, start a new solve, which computer to run it at, and how many cores to use per project. So if you had multiple projects, they would be listed here, and you can prioritize which ones to solve here as well. But for us, we'll just run this one model here. We'll go ahead and hit run. What's happening now is there's a new window that opened up. Here, let me pull that up. This is the solver window. By default, you'll have the info window open, which shows you the total cell count. As you can see, it already meshed the model just in a few seconds. We have about 260,000 cells, 108,000 are fluid, 150 are solid. We also have a log, which has some timestamps, and these little windows are activated with these two here. Now, we can also visualize how the model is solving through these other icons here. So let's go through those one by one. First, insert goals table. This shows what the current value is of our goals that we set in our project, as well as the convergence progress. Okay, so we'll leave that open down here. Next, we have the ability to insert goal plots. So if you have a lot of goals, you can search from here. In this case, I know I just want the junction temperature, as well as some of the global goals that I have set previously. Hit OK. And here we can monitor our goals and how they are converging. Now, if you right-click here, you can change if you want iterations, travel, CPU time. If you have transient set in your model, then you'd have your time steps available here as well, along with other viewing options here. You can minimize this. And lastly, we can show a preview cut plot here. So here you define which plane to use. And if you go back to your model, you can see where that plane lies on your geometry. So in my case, I want to move it right about there at the U1 component. So let's go back to the solver window. And I know it's about 70 millimeters. Let's go back to the model, and we can see that it is lying right through the middle of that U1 component. So I'm happy with that. Under settings, I'll change pressure to temperature. I'll up the resolution a little bit and hit OK. Now it's showing our whole computational domain size. I can modify that cut plot here. You can right click and go to properties. For one, I want to trim our cut plot, so I will reduce the Ymax size to 150. Hit apply. I'll also reduce the Ymin to -50. There we go. Some other options here. You can also display mesh and hit OK. So once these have been created, if you resolve your model, these windows will be saved for next time you solve. Okay, the solver finished. You can see our goals have been converged. Our goal plot shows that our goals that we've selected are now steady and no longer changing. It took 7 minutes to solve on my laptop here. And at this point, we can close this window. Now that we've solved the model, let's look at post-processing the results. First, let's look at the graphical analysis of the results, and then we'll look at numerical data after that. So here in our tree, we see under the results branch, we have a number 1.fld. That means we have some results loaded. You can also see in the top middle of your screen here the number of iterations that it took to converge this model. So let me minimize the input data branch, and let's look at a handful of these different post-processing features. To start with, let's create a cut plot. We can right-click Insert. This pulls up the Cut Plot Properties window. The top section here is for selecting where we want the cut plot to go. I'll select this middle one and select the YZ plane. You can move the cut plane this way or graphically by pulling the arrows here. For display, I'll leave contours on. You can also add isolines, vectors, streamlines. You can also apply a mesh here. For contours, I'll change it to temperature. Under options, I will uncheck the use CAD geometry so that we actually see what FLOEFD solver sees as far as the geometry goes rather than displaying the CAD geometry itself. And then you have different viewing options here. Hit OK. I'll come up here and hit display, which will hide the CAD. You can always click on it again to bring it back. For this cut plot here, we can modify the properties of the cut plot here in the legend as well. You can also move the legend anywhere you'd like here. If I move my mouse to the left, I can increase the number of colors that it uses in the cut plot. I can select and drag the maximum value used in the legend. Or if you click on this arrow again, you can reset the plot maximum here. Hit OK. You can also do the same for the minimum here. There are other visualization options by going to right-click Appearance, where you can modify the text, palette size, background, and so on. If you also hover over the scalar temperature, you can change the scalar just by simply selecting here and hitting OK. Now I can also right-click here on this one, hit Clone. We'll edit this one. And let's do XZ plane, hit OK. And if I select the cut plot 2, a little pull handle appears, which I can now drag anywhere I'd like without having to open the property sheet of the cut plot. Now I can change both of these plots scalar by going here, hitting OK. You also have a probes feature here. If I select that, it'll show you the temperature right on that cut plot. If you left click, that probe will stay here. You can also adjust the probe call out location by left clicking and dragging. If I want, I can also bring back the geometry, maybe make it wireframe. Okay, now let's look at surface plots. First, let me change this back to solid. I can select both of these, right-click and hit hide. I can also go over to probes, and I'll click on display probes to hide those two. For surface plots, you can right-click, hit insert. Let's say I want to select just the PCBs. Let me expand the input data, and I'll select these two. I'll do contours. I'll change this to temperature, solid, increase the number of colors to use. Let's say I want to take a look at the mesh as well, and hit OK. I'll hide the CAD geometry again so I can see the surface plot in clearer detail. Now if we right-click here, go to Edit, we can also change the color palette. So let's select the first one here, and hit OK. Now let's take a look at flow trajectories. We'll right-click, hit Insert. For starting point, you can choose points on the screen, coordinates. I will choose this starting from a shape option. By default, it has a line. I'll change that to rectangle. You can adjust the size of your shape. So let me make that somewhat smaller, about the size of the enclosure. And also, I'll slide it down to the bottom of the enclosure. I'll give it more points. Let's do 100. and I'll make the arrowheads a little bit bigger, 2 millimeters, and hit apply. I'm okay with that, so I'll hit OK. And if you right click on this flow trajectories, you can hit play. And just as before with the other legend, you can modify this legend here. You can change from velocity to temperature. Hit OK. Change the upper limit to the plot maximum. Okay. Going back into the flow trajectories property sheet, you have the options to change the appearances, place constraints on it, and crop the region as well. In this video, we'll review the results numerically. The most common way I like to do that is go to Goal Plots, right-click, Insert. Here we can select which goals we want to review. If you have a lot of goals, there's a filter option on the very top that can help you with your selection process. Here we can decide what we are going to plot our goals against. So CPU time, iterations, travels. If you had transient set, there'd be time steps here. We'll check on group charts by parameter. And then you have two options to display results. One is export to Excel. Here on one tab, we have the list of goals we have chosen, the value, which is the value on the very last iteration, minimum max values, progress of convergence, and so on. Other tab shows our temperature versus iteration graph. And our plot data is the numerical value at each iteration. Okay. Now if we click Show, we can see the same data we just saw in Excel, but within FLOEFD in this separate window here. So here we have the results in the table, and then if we go to History, we can see the convergence graphs here. Okay, now there's also a third option. If we OK these, and if we right-click here and hit Show, that data is also shown here, built into the graphical area here. If we right-click, you can hit Display and change that to Summary to see the numerical results here as well. If you had forgotten to create a goal before you hit Solve, you can still extract numerical data from objects in your model. These parameters can help you do that. So for example, if we right-click on Volume Parameter, hit Insert, we can select which components we want to pull results from. In this case, let's say I want to select all the packages in the model. As we saw before, we can go into our input data, select the material that has that geometry assigned, or go to the Creo tree and select it. But I want to show you another cool feature here. So if we select Use All Components and then Filter by Domain, we can then decide whether to remove or keep any components with the materials we select here. So for example, if I want to keep all the packages, I can select the typical plastic package, which is what I have the packages assigned to, hit Keep. And now that will select all the components in my model. This is a very useful feature when you have hundreds of objects in your model. I'll select temperature solid and click Show. Now using volume parameters rather than goals, we don't have the option to see the convergence graphs, but the numerical results are here. And then you can also export to Excel. And it's also displayed here on the graphical area where you can show or hide it here. Another numerical/graphical way of processing your results is called flex plots. So let's take a look at that. We'll insert that. You can select which components to use. In this case, I'll just say all components. Hit OK. You have the option of filtering by power. So I'll just set that to a minimum of 1 watt. And you can group objects here too. So let me just, for the sake of this demo, group the PCBs separately here. And for what we want to display, I'll check off the volume sources nodes. I'll leave the radiation, computational domain nodes, and fluid nodes. Let me update this. And here we can click and drag. So let me get the PCBs here on one side. Fluid subdomain out here, computational domain. So what this shows is how heat travels through your model. So if we follow one PCB here, we can see that 4.2 watt leaves through thermal radiation. We have through conduction here, 4.5 watts leaves into the gap pad, and then that 4.5 watts goes into the enclosure, where from the enclosure we have 9.8 watts leaving the system. Compared to the other PCB where I believe we had the gap pad directly on the component rather than behind on the PCB, we have 2.3 watts going into thermal radiation, 4.8 watts going into the gap pad, 5.3 watts going into the enclosure, and so on. So it's very customizable, and it's a great way to look at the overall heat transfer path for your complete model or for the components that you select. The last thing I want to mention is the compare tool, which allows you to compare different projects' results numerically and graphically. So for example, let's say I have two different projects here. Let's quickly create one. I'll hit clone, hit OK. And in this new project, let's say I have some different heat sources. Maybe I'm going to attach a different material here for the gap pad. Let's say I go under predefined interface material. Just select a random one here for now. Now I have a different material. I'll hit run, solve. Now that the model is solved, we can go under results and compare. Here we can select what we want to compare each project with. So for example, our cut plot, our gold plot. Select which projects we want to compare with. Hit compare. We have our tabs generated here with our cut plots, where we can edit how we want to view them, and our gold plots here comparing the two projects' results. We're looking at the history convergence graphs.